Okay, hello everyone. Let's quickly look at L'Hopital's rule. It's very, very simple. So what does L'Hopital's rule tell us? Usually in the exam, you would be given a scenario where they say you evaluate the limit using L'Hopital's rule. So what does it mean? It simply means the following. It means as x approaches some value, let's call it 0 in this case. Let's say we have x over 2x. Well, in this case, if I direct substitute it, I get 0 over 2 times 0, which is 0 over 0, which is undefined. That's our first scenario. Our second scenario is the following. We have, again, let's do this. We have infinity over 2 times infinity. So that gives you infinity over infinity. Now, whenever if we see these two conditions, that's the only two conditions where we see 0 over 0 or infinity over infinity, we can then apply L'Hopital's rule. So what does L'Hopital's rule tell us? Well, L'Hopital's rule is simply the differential. So in this case we had, look, the limit as x approaches 0 for x over 2. We can simply rewrite this as the differential from the top. So the differential of x is 1 over the differential of x. In this case 2x is 2, so then we just get 1 over 2. So that's actually our final answer, 1 over 2, and not 0 over 0. So that's all you do when you find 0 over 0 or infinity over infinity. You use L'Hopital's rule. That's literally it, nothing more to it. Now be aware that you differentiate the top as a, you can sort of think about it as two isolated functions. So for instance, if you get this, the limit as x approaches some value for a over b, differentiate a and differentiate b separately. Don't get confused. I've seen only one student in my entire teaching career though get confused and using the quotient rule to differentiate the L'Hopital's limit, which is obviously not what we want to see. You know what I mean? Anyway. So now that you understand the basis for L'Hopital, let me do 5 examples. First one, the limit as x approaches 0 for x squared over sine x. Now check this out. If I substitute, I'm only going to do the substitution once because you should be able to catch it. I'm assuming the students that's watching my video are all top students. Just kidding. Anyway, we got 0 over 0. So since we get this condition, we can now apply L'Hopital's rule. So let's do it. The limit as x approaches 0, the differential of x squared is 2x over the differential of sine is cosine x. Now look what happens now. By the way, we keep writing limit up until the point of substitution, then you stop writing it. So now we can say 2 times 0 over cosine 0, which is then 0 over 1. So this limit is 0. Okay, so there's your final answer. Easy stuff. As I mentioned earlier, the only thing you could do wrong here is you don't know how to differentiate. Okay, let's look at the next one. So in this case, we have the limit as x approaches negative infinity for 3x minus 2 over ex squared. Okay, so if I substitute negative infinity here, I get infinity over infinity. It will be positive over negative infinity, or the bottom will be negative, right? This is going to be negative infinity over positive infinity. So we can then apply L'Hopital's condition. So we need to differentiate this e to the x. If you're not familiar with how to do this, you can sort of think about the entire function as f of x, and you can think about the top part of the function as g of x. So how do we differentiate ex? So for ex, you can just think about it this way. Maybe let's make this gx. So you can sort of think about it as the f of x times g prime of x. Okay? Or you can just, I would assume that's the easiest way to think about it. So in this case, we have the limit as x approaches negative infinity. Let's differentiate 3x minus 2, that's 3. Differentiate the top, I'm just going to rewrite this, times the differential of the top, that's 2x. And if I substitute negative infinity in here, If I substitute negative infinity, I get that will be infinity. So that will be a very, very large negative number. So I'm going to write it as 3 and then over a large negative number. And when this is the case, right, because look, that's going to be positive infinity. I'll just do it here quick. Negative infinity. So that's going to be, look, infinity squared is positive infinity. E to the infinity is infinity. So that's just going to be infinity times negative infinity, which will give me negative infinity, which means this number is approaching a large negative number. So I'm going to write it like this. And whenever you see this particular case, we then know 3 over a large negative number will eventually be 0. So that's how you would answer this particular question. Let's look at the next ones. Okay. Find the limit. Now for this one, there's a couple of ways you can actually solve it. I'll just solve it using L'Hopital's rule, of course, because that's what we're doing here. However, you could factor out the x square. That's a more common way, factoring out the x square. However, that wouldn't work if you if you have to get the points using L'Hopital's condition. Anyway, let's see. Plug in infinity, infinity, infinity. We get infinity over infinity. If that's the case, we can apply L'Hopital. So which means I'm going to differentiate the function once. So we get 6x plus 1 over the differential of that's 0, the differential of that's 1, the differential of that is 6x. Here we get 10x plus 8. However, if I substitute infinity in, I get infinity over infinity again. So this is called the repeated use of L'Hopital. So now we can just do it again. We can just we can reuse L'Hopital. You can use it multiple times, by the way, as long as the condition is met. So it's going to be 6 over 10. So my final answer will be 3 over 5. And by the way, out of interest's sake, whenever you see a quadratic or a cubic function that's approaching infinity, your answer will always be the leading coefficients over one another. So that's how you can confirm your answer. It will always, always, always be the case, provided your degrees are the same, both top and bottom, and you have leading coefficients. Okay, so the next one, the limit as x approaches infinity. So we got x raised to the negative x. Okay, first things first, I'm going to first write this in a more appealing way. So that's e raised to the x. If I substitute infinity here, I get infinity over infinity, so we can apply L'Hopital's condition. So that's always what you want to look for, by the way. You want to first try figure out how can I create L'Hopital's condition. For instance, one example, I know this is a side note, but this one, so this is a very, very, very common question. The limit as x approaches, I think it's 0 or infinity. I think it's this one, for x, ln x. So you might then think, I think it's 0, I think it's 0. No, it can't be 0 because that's undefined. Anyway, so it might be infinity, so you get infinity, infinity. But then you can actually rewrite this limit as, because x can be rewritten the same as 1 over x. It's the same thing. If you don't understand this, I'd recommend go watching maybe like a grade 8 fraction video. I don't mean that in any rude way. If you do find that offensive, my apologies in advance. So I can then rewrite this as the limit as x approaches infinity for ln x over 1 over x. And now if I substitute infinity, I get infinity over infinity. And then in that case, we can just differentiate this function. So now I can say, well, the differential of ln x is that. The differential of 1 over x is usually negative 1x squared. And then we can multiply both top and bottom. I know I'm going off track here, but I think this is very valuable lesson. Swap these two around. So these 1x cancels out. You can do the math by yourself. So it's going to be negative x. And then you plug in infinity and then you get negative infinity. You see? Haha. Just wanted to show you that. Because this is a pretty similar case, right? It's a very, very similar case where you have... it doesn't look like it's in L'Hopital's rule, but you can write it to go into that. Anyway, let's differentiate. The differential of x is 1. The differential of ex stays ex. So we get 1 over e raised to the infinity. And we know 1 over infinity tends to approach 0. Okay, very nice. Now we got the final one. This one's a little bit more advanced. So this would be maybe high school. Very likely in university, by the way. But maybe high school, maybe. I don't know. Anyway, so we're approaching 0 from the right-hand side. So let's write that. So x is approaching 0 from the right. And then we have cotangent 2x times sine 6x. Okay, very interesting example. I remember just taking it. Let's see, what can we do? Okay, we can rewrite this as the limit as x approaches 0 to the right. Cotangent we can do two things. We can write cotangent as 1 over tan 2x, or we can write it as cosine 2x over sine 2x. However, I don't think I want to use this one, because above the bracket we'll have sine cosine, and that will be 0. But sine 0 is also 0. I guess we can do anyone. We can use either this or this one. Both are actually fine. However, I'm going to use 1 over tan because it makes it a lot easier. So it's going to be 1 over tan times sine 6x. So I'm just going to write it. Sine 6x over tan 2x. And now if I plug in 0, I know that tan 0 is always 0. Sine 0 is 0. So we get 0 over 0. So we can apply L'Hopital's condition. L'Hopital's rule. Differentiate sine. How do we differentiate sine? If there's a single number here, just bring the number forward and change sine to cosine. Very, very easy. Cosine 6x over the differential of tan is secant squared x. So we get 2 secant squared 2x, sorry. Secant squared 2x. And then I can now plug in my zeros, because I know both for cosine and secant, both of them contain a cosine, so it's going to be 1. So that's fine. So for secant, it's going to be, so look at this. You can write it like this if you really want to. And then if we plug in, sorry, this 2 is supposed to be, no, it's below, never mind. 1 over 2. So that's just 1, very simple. However, I'm going to plug it into secant. So it's going to be 6, 0 over 2 secant squared to 0. And then you see when I plug in my 0, I stop writing the limit. So in that case, we know this is 1, so 6 times 1 is 6. The secant square is also 1, so that's going to be 2. So my final answer is 3. Okay, that was L'Hopital's condition. Very, very, very easy stuff. This in the IB exam, this is 3 points. I'm not even going to lie to you. The only thing that's a bit tricky about L'Hopital's condition, or L'Hopital's rule, sorry, I keep saying condition, is if you don't know how to differentiate. If you don't know how to differentiate, then as I mentioned in all my other videos in the HL, you are done for, you know. But don't give up. Don't give up. Still lots of time to learn, but ensure that you understand differentials. Otherwise, you know, you struggle with this, you struggle with Euler's method, you struggle with Maclaurin series, Tyler series. You know, there's a bunch of things you struggle with if you don't know how to perform differentials. That's why your teachers probably give a lot of attention to it. Okay, anyway, quick recap. First things first, If you see a limit, they tell you use L'Hopital's rule, you know the answer is always going to be 0 over 0 or infinity over infinity. If you find that, differentiate. If you if you find infinity over infinity or 0 over 0 again, you do it again, differentiate again, and you just keep doing it.